All right. Hi, everyone. My name is Spinale. Until recently, I was part of ARM Research, where I led the IceCap project, which I'll touch on later, but I've since gone independent. And as Gerwin said, this is a less formal session. I'll talk for the first part about where we're at. Sorry, it's about Rust support and seL4 userspace, obviously. And what I think we should do next, and then the rest will be discussion. But I think it'd be good if we had discussion throughout as well. So please feel free to interrupt me at any time and we'll talk about what's on the slides. So first, I'll try to motivate or justify all this attention on Rust. We know that that memory safety issues account for a large portion of vulnerabilities in C and C++ code. Microsoft estimates that number to be about 70% for its own software, and the Chromium project makes a similar claim, but I don't need to convince you all of this. High-level languages like Rust enforce memory safety, but Rust distinguishes itself among other high-level languages by providing great support for running in less rich environments, and I'll talk more about that later, and for not requiring a heavyweight runtime system. Rust provides memory safety enforcement using compile time analysis of variable lifetimes and pointer usage, sometimes with the help of the programmer in the form of annotations, instead of a garbage collector. And here's just a really quick code example. The variable R is attempting to refer to X, whose lifetime is only limited to the inner scope, and the compiler catches this and emits the error on the right. More generally, Rust aims to provide its high-level language features like closures, Haskell-style type classes, and library-level green threads with minimal overhead, and the documentation refers to these features as zero-cost abstractions. And thanks to these design decisions, we're seeing Rust deployed in servers and microcontrollers and in application and kernel code. Speaking of, a little over a week ago, Linux merged support for Rust as a second language inside the kernel. And I think this is a pretty big deal for the Linux kernel, but also for Rust. It assures us, us in this room, first off, that Rust is ready for us. And it also means that support in the Rust ecosystem for running in less rich environments is only going to receive more and more community attention. And so this is good news. But let's turn to the seL4 user space. What Rust gives us here is a high-level language that is useful even for the lowest level components in our user space. Those without access to comfortable OS services, and even for resource-constrained systems. And just to illustrate that bit about the lowest level components, as part of IceCap, we got just a pretty rudimentary port of the Mirage OS unikernel, the OCaml unikernel, running on seL4, and a lot of that glue code was actually written in Rust. So, and it's feasible to have, or it's actually easy to have an seL4 user space without a single line of C, just Rust. So that tells you that you don't need glue code to support it. It's suitable even for the lowest levels of our user space. And I should emphasize, this has been brought up before, but what I'm talking about here is for unverified user space code. We know that the tools for Rust for verification aren't there yet. There's a lot of interest, but they're not, obviously they're far behind C. So I'm talking about how we can strengthen unverified user space code. And the reasons why Rust is a great fit for the seL4 user space are similar for why it's a great fit for the Linux kernel. Obviously, memory safety allows us to write unverified components more reliably. Higher level language features allow us to use abstraction to develop systems more efficiently. And crucially, code reuse becomes much easier. And now with Rust in the Linux kernel, we're hearing ideas in that community about new drivers, the ones that are going to be ones written in Rust moving forward, being designed in kind of a modular way where the generic bits of those drivers might be factored out of the Linux specific parts and made available separately. And that would be a pretty big deal for us here. And as I mentioned before, Rust distinguishes itself among other high-level languages by having great support for running in less rich environments. For example, the Rust standard library is split into 3 parts. One part which requires operating system services like a file system, one part which requires just a heap allocator, and one part which requires nothing at all. And lots of libraries throughout the ecosystem can be configured in that same way, depending on what your program has access to, whether it has access to OS services or a heap or nothing at all. And as a kind of remarkable result of all of that, or I would say more of a byproduct, getting Rust in the seL4 user space doesn't really require any porting at all. There's one exception at the kind of like last optional step that I'll talk about in a bit, but doesn't require porting any code. But let's talk about now what it does entail. There are a number of projects throughout the seL4, a number of open source projects throughout the seL4 ecosystem that use Rust in their user space, but there's not a lot of support upstream. There's almost none at this moment. And I mean the seL4 upstream, not the Rust upstream, just to be clear. And so what I'm going to do is I'm going to present a mental framework that I use for thinking about a complete story for Rust in the seL4 user space. I'm going to talk kind of abstractly, and this is kind of, just a way of thinking about it. And then I'll talk about all the existing projects in terms of this framework, all the existing open source projects in terms of this framework, the ones that I know about at least. And so I like to visualize this this hypothetical stack, this work to be done as a pyramid, where at the bottom we have layers that are unopinionated and really generic, and then as we move up, we have layers that are dependent on the previous layers and are more opinionated, and implementations of them might be less widely applicable. And so at the bottom we have just the lowest level expression of the seL4 API in Rust, and this would be in the form of a library, which in Rust is called a crate, and that crate would be called libseL4sys, according to a Rust convention that I don't think is worth talking about now. But this is probably pretty familiar. This code looks just like the C seL4, libseL4. It's not very interesting. But there's a question to be asked about how that code is generated, whether it's derived from the C headers and linked against the C static library, or whether it's kind of generated in parallel with the C libseL4. I think the sweet spot is right in the middle, but we'll only talk more about that if our discussion leads us there, because that's kind of in the weeds. At the next level up, we have a higher level expression of the seL4 API and the basic constructs you can get immediately after that. And I think that for a general story, or a widely useful story here, this would need to be unopinionated, dependency free, and but while still leveraging the high level language features we have in Rust. So here's just a really brief example that I won't talk too much about. But in this example, we use kind of idiomatic Rust error handling flows. You can use smart pointers to manage write access to the IPC buffer, and more smart pointers to get kind of ergonomic synchronization constructs right on top of notifications. And so now on top of all that, we have the language runtime, and I've talked about how Rust doesn't require much of a language runtime at all, and strictly it requires almost nothing, but seL4 tasks will probably need some kind of initialization, like setting up thread local storage and initializing IPC buffer pointers for lower levels in the stack, just kind of basic stuff. But tasks might also need a heap allocator or exception handling by stack unwinding. I consider that to be part of the language runtime. And once at this level, you can write a task. Here is one of them. And I think for this level to be, for an implementation at this level to be useful to as wide a range of potential projects, it would need to be very configurable. And it would need to be configurable along many axes. For example, whether the task requires a heap, whether that heap is static or dynamic, and whether the task itself is managing the resources that back that heap, whether the task requires exception handling by stack and winding, whether it's a root task, and if not, what kind of environment it's running in, and what debugging facilities are available to it, and how those can be accessed. And that's a lot of configurability, but in my experiments, I've concluded that it is possible using a range of different by using abstraction at a range of different levels in the program and the build system. Just for the sake of time, I won't talk about this part. So after you have the groundwork laid down, you can start creating reusable kind of richer building blocks for building systems. So for example, think the kind of stuff we have in seL4 libs for dynamic resource management, drivers, and virtual machine monitor. And eventually you have to start composing your system together, weaving the tasks into a complete system. And, think CAM keys or the seL4 core platform. Though it takes some work to get this working with Rust, and there are also kind of new things you can think about doing. And then optionally at the top, this is the only porting task you'd have to do. This is libstd is the name of the part of the Rust standard library that I mentioned before that depends on OS services. And if you port that, then now you can use Rust libraries that depend on that, Rust libraries that don't have a configuration for less rich environments. And for example, in IceCap, we did this to be able to use WaSMTime, the WebAssembly JIT compiler and runtime, and that worked. And again, there are different ways to do this, but I'm not going to go into detail on this right now, just for the sake of time. And then on the side, where no one wants to look, we have the build system. But we all know that that is still important. It impacts developer experience, and we've all had developer experiences with build systems. But I think beyond that, a good build system is an important part of rigorous engineering. You need to be able to properly assess your system. You need to have a good understanding of what code is actually being built and run, and exactly how it's configured and where it comes from. So I think this is important. And when you introduce a whole new programming language, a whole new, the world of Rust into your build system, that adds a lot of complexity, but there are ways to manage that complexity. One idea is an idea that folks working on the seL4 core platform have also had, which is kind of decoupling the build for the kernel from userspace. And I've been experimenting with that as well, and I think that that's a good way to go. But enough with this kind of hypothetical pyramid. Let's talk about the, I'll briefly talk about the these 5 open source projects in the ecosystem already in terms of that framework, and I'll go kind of fast so we have time for discussion. Robogalia was the first, started in 2015, back when writing Rust code for less rich systems was a lot more difficult. And the scope of Robogalia is an entire seL4-based operating system. At the building block level, it includes libraries for dynamic resource management. And at the libseL4 sys level, it includes a pure Rust solution, which I'll talk about later. And Robogalia is a very ambitious project, and even though it's not super active now, we see it constantly coming up in these other projects. Next is seL4, which mostly is focused on build system automation. What it brings is a tool for kind of encapsulating building an seL4 kernel along with its user space. And it's not active anymore, but some of its best ideas have carried into the next project, which is Ferris, which we'll be hearing more about later today, and I'm excited for that. So I'll talk only very briefly about it now. But its scope is broader than seL4, and even though it does include an evolution of some of the ideas of seL4, but it also has some really awesome user space libraries that allow for compile time, resource management, tracking, and we're going to hear all about that today. Next is IceCap, which is a project from ARM Research that I led while I was there, and its initial purpose was to explore virtualization-based confidential computing. So it's a hypervisor based on seL4 that I presented on in the 2020 summit. I probably should have linked that presentation here, but I forgot. The code is separated into the generic bits that could be useful to other projects. We call it the IceCap framework, and then the hypervisor itself. And right now, the project, its focus has shifted away from the hypervisor and the framework and more towards applying some of the ideas we developed to some exciting new technology that I'm not really sure to what extent I'm at liberty to discuss here. But the home of the code of the IceCap framework, which is the part of that project that is most relevant to the discussion, is a little bit up in the air. But I've been working with the team at ARM and using some branches of it as a testing ground for a lot of the ideas that I've talked about here. And you can find those branches down at the bottom, if you can see. And finally, most recently, we have CatOS from Google. Phase 1 of its open source release was August of this year. And at the libseL4 sys level, it builds on Robogalia's pure Rust solution, and they actually managed to upstream some relevant build system bits, and so that's great. And at the framework level, they use CAM keys, and their highlight, in my opinion, is their capdl loader, which is written in Rust, which is able to reclaim the root task's resources, which means that it's suitable for very resource-constrained systems. And I'm excited for the kernel changes that were necessary there to be upstream. So yeah, just that was a quickly touch on all those. And I hope that we can pool some of our ideas and resources to implement some part of that pyramid upstream. And I think it'll be really important for us to keep in mind that especially the lower levels should be implemented in a way with kind of broad applicability in mind. And I kind of mentioned that when I was talking about all those levels. This pooling of ideas is already happening online. Join the discussion on Discourse, but now I think we can transition to the discussion here, and I'm happy to answer questions, but I think we should try to forget that I'm facing this way and all you guys are facing that way, and maybe try to, yeah. But I'm happy to answer questions if that's the structure that we want. So yeah.
Thank you. First, a round of applause. And yes, we have some time for discussion. If we have to cut off at some point, it seems very likely that there's going to be one of the birds of a feather sessions will be on Rust this afternoon as well.
Great.
Okay, first question. Kent in the back.
Thanks for the talk. Going back to the slide where you had the stack, your mental model of Rust support in seL4 ecosystem. Do you have any opinions about whether the right way to approach adding Rust support would be bottom up, which would be starting with seL4 sys, or top down, maybe starting more with a particular framework?
That's a great question. And my answer might be basically the groundwork is not a lot of code. It's not a lot of code, and it all exists, and multiple versions of it exist. And so given that, I think that bottom up, there's not a lot of cost to it. And when you do it that way, the higher levels, you get the benefit of having them be thought out with the whole thing in mind.
Right, but then like when you're building bottom up, you sort of have to envision the possible frameworks that are going to be built on the top.
That's a good point. when I've approached this kind of problem, I've done so with minimality in mind, making the fewest assumptions about what's on top, and trying to design things where if there's lower level stuff that needs to support the stuff on top, that it can be added on the side. If that makes sense. That's so vague.
I think I understand.
Yeah,
It's like you're talking about, just start with something that you already think is generic enough, but then accept that you have to evolve it.
Yeah, like for example, for the language runtime, for initialization, you know what that looks like for a root task. It's almost nothing in this case, but for when you're running in a different kind of environment, you might have, who knows how information about a task environment is going to be provided to it. So the approach that I've taken, and one solution that I've drafted for that is like just having a generic interface to plug in there. Again, I'm being so vague, but we can. It's a good point.
Because I guess I was like sort of pointing out one of the things with the current approach is we're sort of starting from the bottom, and this is like on the discussion. Whereas like another approach of starting from, say, something like picking CAM keys or core platform and saying, okay, what will it take to add Rust support at that level, and working down, and then you've done the same thing already for IceCap, which sort of gives you the perspective of what you needed for IceCap at the top, and then building up from there. But having a few independent framework support, at that point, you have enough stuff to sort of consolidate at the base, and then have a generic enough thing that you can overwork for all of them.
Yeah.
So I would, if I can butt into the discussion, I would say, since I have the mic, we might actually be at that point already, because at least for the bottom two layers, the problem is more one of consolidation than of coming up with a new one, right? We have like Robigalia, IceCap, the Google system. All of them already have an implementation of those layers, and so we have a few examples of what we need to be generic in.
I think IceCap is the only one, and maybe I'm even being too generous, that you're actually building proper applications on. Whereas like Robigalia it's still a starting point for an OS, and so it's like you're building the framework or the baseline support for the stuff that you could build in the future, but you're not actually building the stuff in the future to drive that design.
Okay, I thinking about your original question a little more, and what you just said, the framework level, at that level, I think it makes more sense to not just do it, aspirationally, but for the lower levels, I think, especially these two levels, the bottom two levels, I think there's not a lot of, I think you can make them really unopinionated. But when I answered your question initially, I wasn't really thinking so much at the top. And I agree with you. I think at the framework level, you have to have a much better idea of what you're going to actually build, or else you're not going to make something very useful.
Yeah, I'll hand the mic back.
All right.
All right.
We'll talk more.
Would somebody else like to talk? Okay.
So I haven't played with Rust for a while, but watching what's happening on GitHub, and what comes up a lot is Rust really wants a dynamic libseL4 that has a dynamic configuration, whereas our model is usually, here's a static configuration, and you get a different build for different versions of the library. Do you have any thoughts on if that's resolvable?
Yeah. So that's a really good point. And that's part of the discussion that's happening in that on Discourse, and I'll give I'll tell a story that I think is one possible solution to that. So I think a way, instead of talking too abstractly and not answering the question very clearly, I'll just be really concrete. I think one solution is having not having any Rust specific code living in the kernel build, and having the kernel build output, libseL4, which is partially configuration dependent, and of course the libseL4 configuration, and then maybe some intermediate representations of this, of kind of the XML or bitfield sources that the libseL4 sources are generated from, like that's already kind of pre-processed and easier to digest, and then the Rust libseL4 sys build system, build script can consume those, and is that kind of a story that resolves the question you're talking about? All right. Okay, yeah, sorry, maybe you misunderstood.
Okay, next question here.
Yeah, so putting on my verification person hat, we've talked a lot about applications. So how does verification fit in here?
That's a great
I want
question.
to integrate my verified Rust code with verified seL4 guarantees. Is there what are you envisioning?
Well, no, sorry.
No, you go.
Well, actually, at the beginning I said I shouldn't just be answering questions. You're probably better.
All right. So, do you have verified Rust code?
I myself am very skeptical of that. I have a friend who's super into SMT verifying Rust. So I guess I'm asking in memory of him. He's not dead yet, but in his spirit. That's what I wanted to say. Not in memory, in his spirit. So yeah, I have a friend who are like super into verified Rust. So how can we go to them and maybe like make this a cool thing for them?
Okay, so slightly more seriously, there isn't really a consensus yet on what verification techniques for us should look like. There is a whole bunch of projects and some pretty cool ones. Maybe I know your friend. I'm not quite sure. But so this framework yet has not really any opinion on how it should be verified and so on. One of the big problems in verifying user level code is that user level code is immediately concurrent code, whereas seL4 code is pretty much the only sequential code in the system, and even like on a Unicore system. So that makes it kind of complicated, and you would need a concurrent system level model of what's going on before you even talk about what a specific language does with that. But given that, yes.
Cool, thanks.
Okay, there was one more question in the back, if you still have. All right, okay, good. Anybody else? Or we can talk about that config question. I will give you the one, and then we can conclude.
Right. To answer the earlier question about aligning the configuration between what seL4 needs and what your Rust projects need, both FEL4 and the underlying library for Pharos, selfie-sys, use build utility level libraries to align the configuration flags between the cargo package manager and the flags that get sent to the seL4 build system. So